Let's talk a little bit about speed. Here is a sample calculation that I'm sure you have done over 100 times just in your head while you're driving. So I'm not going to give you an equation. I want you to realize that you know how to solve this without me telling you. You know what to do. You might not even realize you're doing an equation, but you can figure this out. So press pause, take however much time you need to answer this question for me. Okay, so what you did, even if you didn't realize it, was you used this equation. You calculated your average speed by taking the total distance that you traveled divided by the time interval that you spent traveling. So you put 300 miles on the top, you divided that by 5 hours, and you found that your average speed was 60 miles an hour. So you do this all the time. You might not realize it's an equation, but that is an equation. We're going to not talk as much about speed. We'll talk a little bit about speed, but okay, let me get to it. So speed, as we're talking about here, is a scalar. And in 2 weeks, we're going to talk more about the difference between a scalar and a vector. So for now, when I talk about something that's a scalar, what I want you to think is there's just a number. So speed is just a number. It's just a number like 60 miles an hour. There's no direction associated with it. Okay. When you get a ticket from a cop, you get a ticket for going 80 miles an hour. That's just a scalar. You don't get a ticket for like 80 miles an hour at 23 degrees northwest. That's not, there's no, you're just going, you get a speeding ticket because they just care about how fast you're going, and that's it, not what is your direction. The quantity we're going to worry about more is velocity, which which we'll get to. Okay. So let's look back at our number line. Okay, let's say we have a guy here. He starts here, he's running this way, he's running this way, and that whole thing that he does takes 10 seconds. So tell me, what is his average speed? Okay, take a second and try to figure that out. Well, you would say the total distance that he traveled was 15 meters. So, right, because he travels 5 meters here, 5 meters here, and 5 meters here. So in total, he ran 15 meters. That's the total distance he traveled. The time that he spent traveling was 10 seconds. So you would just do 15 divided by 10, and you would get that his average speed is 1.5 meters per second. If he was like riding a bike doing that and he had a little speedometer, on average, his speed would be around 1.5 meters per second. So this type of equation and calculation, I think, is probably normal to you. It's not surprising that we do this. It's not tricky yet. Okay, but as we're going to learn, this is not the type of thing we do in physics that much. We don't really care about calculating average speed. We're going to care about calculating average velocity. By the way, this is the world's largest thermometer in Baker, California, on the way to Vegas. Okay, so the quantity that we care about more than speed in physics is velocity. Okay, so velocity is very similar to speed. We're going to try to keep them separate though. Okay, so we can calculate our average velocity, which is similar to average speed, but it's different. Not by taking the total distance we traveled, but by taking our change in position. Do you remember what is another word for change in position? That's right, it's displacement. So we can take our displacement divided by our change in time, or the time interval, change in time, time interval, either one. So we can say the average velocity is equal to our displacement divided by our time interval. Do we remember the variable that represents displacement? Delta x. Okay, so we can say v, that's the variable we're going to use to represent velocity, v, and then I put avg down here. I'm talking about my average speed, my average velocity, because we're going to have a difference between our average velocity and our instantaneous velocity, if you remember that from your calculus class. So this is just the average velocity. On average, what was our velocity while we were traveling? We calculate that by doing delta x, our displacement, divided by delta t. Delta t is how much time elapses as you go from x initial to x final. And then we're still just reminding ourselves, what is delta x again? Oh yeah, it's just x final minus x initial. Okay, so let's look at this guy again. We already said his average speed was 1.5 meters per second. That gave us an idea about how fast he was going. His average velocity, though, is going to be pretty different, because when we calculate his average velocity, again, this happens in 10 seconds, we're going to do x final. Where does he end up? He ends up at an x position of negative 5 meters. Minus x initial. Where did he start? He started at 0. How long did it take? 10 seconds. So On average, his velocity was negative 0.5 meters per second. What does that even mean to have negative velocity? Well, remember, to the left is negative. So on average, he was going to the left more often than he was going to the right. That's why his overall average velocity is negative. So this concept here, is not something that you would use in your daily life. This doesn't mean anything to you. What you would care about if this was you and you were running or riding your bike, you'd want to know, how fast was I going? That's what we calculated on the previous slide, the average speed. This is not how fast you were going. This is not related to how fast you were going. This is a different new quantity, okay? When do we want to use this? In a physics class, that's when, okay? So don't worry that this doesn't make sense. You might be thinking, why would anyone care about average velocity when really average speed is the one that's useful? For now, just don't worry about it, okay? We're going to be using this a lot. So let's kind of distinguish again between average speed and average velocity. So these are the equations that we've seen in the previous slides. For now, I'm just going to say speed is a scalar. Scalar means it's just a number. There's no direction associated with it. Velocity, though, is what we call a vector. A vector has two parts to it. It has a magnitude, that's the number, and it has a direction. It could be north, south, east, west. In this case, it could be to the right or to the left. So because velocity is a vector, we can have a positive value if it's to the right or a negative value if it's to the left. Later, when we look in 2 dimensions, we'll be looking at directions like north, south, east, west. Which one makes sense? Speed. This whole thing here makes total sense. This is what you've been doing your whole life. Which one do we use in a physics class? This one down here. Okay. So let's just emphasize this. Look at Usain Bolt can run around the Oceanside track in about 40 seconds, let's say. Okay, so that's 400 meters around the track. He can do it in 40 seconds. One of these values is his average speed, and one of these values is his average velocity. Try to figure out which is which. Well, his average speed is 10 meters per second. That's the number he cares about. That's the number that kind of makes sense. How fast is it? That's super fast. He is super fast. Look how fast he is. 10 meters per second. Super fast. His average velocity is the one that we would care about in a physics class, is 0 meters per second. Because on average, the time when he was like running in this direction gets canceled out by the time that he was running in this direction. Because velocity, we care about not just how fast you're going, but also what direction are you going. The times when he's running in this direction get canceled out by the times he's running in this direction. So on average, his velocity was 0 meters per second. Don't let that freak you out. That doesn't mean that he was standing still. It's just a new quantity and a new concept, average velocity. It's not the same as average speed. Okay? Really let that sink in. He is a super fast guy. He is the fastest guy in the world. But when he runs around a track and starts and ends in the same spot, his displacement is 0. That means his average velocity is 0. Okay, so let's bring the idea of velocity into our motion diagrams. So the arrows that we were drawing, those were actually velocity vectors. If the word vector scares you, just for now, let's call it an arrow. Okay, so the length of that arrow that we drew represents the magnitude of the velocity. Magnitude just means how big is it? And in the case of velocity, the magnitude of the velocity is the speed. Okay, so a bigger magnitude means faster. Smaller magnitude means slower. So let's say we were going to draw a motion diagram of an object or a person that's walking or moonwalking, right? Because you can't tell if they're going forwards or backwards at a constant speed. It would look something like this. This is what we've had before. Now what we're going to do is recognize that this arrow can represent the velocity that the object has as it goes from this position to this one. And this arrow represents the velocity it has as it goes from here to here, and so on and so on. These arrows are all the same length. That means that it has these velocities are all the same. So it has a constant speed. The velocity is not changing. What we're going to do to make our picture a little more descriptive, I'm going to start labeling, and I'm going to call V0. So V for velocity, 0 because in physics we like to start with 0 and not 1. So V0, that's the velocity I have right here. This arrow is going to be V1, this arrow is V2, this arrow is V3, this arrow is V4. Why do I do that? Because later I might want to compare V3 to V1 and say which one is bigger, V3 or V1. Well, in this case, they're all equal. Let's look at something that's speeding up. Okay, so try to draw a motion diagram for something that's speeding up. Doesn't matter what direction it's going. Okay, here's my dots, here's my arrows, and now I'm adding in these velocity vectors. Okay, or they're just labels. So now I can really say, where's the object going faster? Which velocity is the biggest? V4 is the biggest. Well, how do I know that? The arrow is the biggest. So where you have a smaller arrow, that means a slower velocity, a smaller velocity. A larger arrow means a faster velocity. V4 is bigger than V0. V4 is the biggest one.